Welcome to the Evidence Reasons Academy. I'm Salvador Cordova, your host, joining you from virtual, not real, Las Vegas, the Palazzo and Venetian Casino, which are my favorite casinos in all the world. They are so beautiful, and I think Las Vegas is probably going to go. It's going to die as a city. There are just so many casinos all around the world now, and people don't have to travel to this place. And people have sort of lost taste for kind of really nice plush joints like the Palazzo and Venetian. Today, anyway, I'm just blowing off a little steam. I had some eagerness to just nerd out and take a break. I had a insanely busy week. I am tentatively scheduled to have a debate against the Big Bang. I'm taking the position the Big Bang was false. On Tuesday, that's tentative. My tag team partner is Rebekah Davis. She and I have been thinking about this for a while, and we've committed that even if the debate doesn't take place, we're going to make some videos about the Big Bang. In the process, I started opening my physics books, and I offered to her, if she's at all interested, to learn more physics. So whether she watches this show or not, this show is dedicated to her. So I think sometimes reading through this is a little cruel to her, but I've been very impressed. She's been studying physics just like crazy. I'm just like, it's kind of scary. I think I've helped bring out her inner physicist in her, one Friday we talked physics for 3 hours, and the video's here, you could see it. And then privately we had another 4-hour conversation on physics. Just like, Rebekah, what's happened to you? So I think, though, I can kind of cure her of her recent love of physics, because when I'm going to read some of these books, it's just going to be, you'll get a taste of physics. I am trying to revive my forgotten study of general relativity. That was my textbook. I'm being tutored by Dr. Philip Dennis. I call him Dr. Phil. So Dr. Phil is helping me relearn general relativity. He is a young earth creationist, but also a secular scientist, a respected secular scientist who's published in the Physical Review Letters, which is the #1 physics journal in the United States. He published 3 times, as a matter of fact. You don't get there if you're dumb. He is brilliant, and he's a young earth creationist. He understands so much about mainstream cosmology, mainstream science, and yet he's a young earth creationist. He is my tutor. Phil Dennis is somewhat notorious because he came out with criticisms of both Jason Lisle and Russell Humphreys, but despite that, he's universally respected in the creationist community as an expert in the topic. He might be the most qualified in the topic of general relativity in the young earth creationist community. I am extraordinarily grateful and thankful that he has taken me under his tutelage. So he recommended this book by Herman Bondi, Relativity and Common Sense, and I'm just going to read through this. I may totally bore some of you, but well, that's nerd physics for you. On Common Sense, Chapter 7. The arguments of this book, and particularly the last chapter, point clearly to the fact that all inertial observers should be regarded as equivalent, not only in respect of dynamics, as Newton already found, but also in respect of light. In particular, this implies that the velocity of light is the same in all directions, irrespective of the state of motion of the observer, provided only that he is inertial. Okay, so I think, if I recall correctly, I'm getting these obnoxious Microsoft intrusions. If I recall correct, I'm sorry, I had to click. I hate it when Microsoft will, I'm in the live stream and it's going to just send me all these little notifications. It's obnoxious. I don't know how to shut it off. Blasted Windows. Sorry about that. Dynamic means acceleration. I'm pretty sure that's the definition. Let me look it up here just to make sure. Dynamics. Okay, page 6. I'm just going to verify that. For the purposes of textbooks and of university examinations, physics is divided into such subjects as dynamics, the science of force. Okay, so dynamics is the science of force. So when Newton said that dynamics was fundamentally concerned with acceleration, okay, so acceleration, Newton's second law, force equals mass times acceleration. You can describe dynamics in terms of acceleration or force. Force is probably the more complete, but I'm not, that's semantics. Okay, I just wanted to clarify that. This result has been stressed before, is indeed obvious once it is agreed that distance measurement should be made by radar methods. For then one measures the time, half the time between the emission and the return of the radar pulse, in order to determine the distance of the target. This time, which could perfectly well itself be used to describe this distance, is a matter of habit, multiplied by a purely conventional and therefore arbitrary number called the velocity of light, merely to express the distance in miles or centimeters. Radar. For then one measures a time, half the time between the emission and the return of the radar pulse. Distance measurement should be made by radar methods. Distance measurement should be made by radar methods. Really, we have also in optical spectrum, EM, lasers. Distance measurement should be made by radar methods. Okay. Also, the principle of the unity of physics requires that systems cannot be distinguished by internal dynamical experiments. Also, the principle of the unity of physics requires that systems cannot be distinguished by the internal dynamical experiments. Also, the principle of the unity of physics that systems that cannot be distinguished by internal dynamical experiments should be indistinguishable by any internal experiments. Okay, so the unity of physics again is page 6. Let me review that. There is the unity of physics on page 6. There is yet another point that emerges from these simple considerations. A great deal is said about specialization and departmentalization, but these very basic experiments and observations in physics that we have been mentioning now exhibit the unity of physics. Keeping with the basic lesson of the unity of physics in mind, we shall easily be able to avoid the pitfalls that misled physics in the 19th century. He basically is saying we subdivide fields of physics, but it's actually unified. I guess he didn't, I don't see how he defined it. Trying to avoid departmentalization. I don't know. Okay. And he also talks about internal dynamical experiments. Also, the principle of the unity of physics requires that systems that cannot be distinguished by internal dynamical experiments, that is, experiments involving force, should be indistinguishable by any internal experiments. Should be indistinguishable by any internal experiments. Okay, so all right, now I see it. If one experiment is indistinguishable, all experiments are. If one experiments in dynamics is indistinguishable, then all other experiments would be. And so, what are other kinds of experiments? Well, if you don't have something involving force, you just have motion without force. Okay. I think is that kinematic? I don't know. Anyway. Also, we are driven virtually without means of escape to Einstein's principle of relativity. All inertial observers are physically equivalent, and no internal experiment can be devised that discriminates in any way between different inertial observers. And I'm going to be confronting Dr. Phil, and he's also teaching me, but I have to just say I disagree with that, and let's work through the math. And I specifically brought up the radar gun experiment. Because I think this can be done I think it can be done. You can build a thought experiment. It may not be practical to actually build an apparatus, but I think you can actually determine what velocity you're traveling at relative to the rest of the universe. Put more simply, it says there's no way of appreciating the velocity of one's vehicle unless one looks out the window, provided the vehicle is unaccelerated. Provided that the vehicle... I think it can be done internally. So I'm going to have to raise page 62. Contemplating this great principle of physics. Okay, again, you've seen me derive the Lorentz transformations from electromagnetic theory. People don't realize the Lorentz transformation was developed as an ether alternative to the Michelson-Morley experiment. It's not usually characterized that way in popular and also textbooks, but that transformation reflects both, what was it, the Lorentz Fitzgerald space contraction and then one other effect, frame dragging. It was brilliant. And today it's used to describe SR, and a lot of people are like, oh, that proves relativity. It's like, or it disproves the ether. That was actually, as best as I know, correct me anyone if I'm wrong, that was an ether-based relativity, not the Einsteinian. It's Lorentzian. Contemplating this great principle of physics after 59 years, one cannot help wondering how people could possibly have thought differently. To say this is no disparagement of the tremendous achievement of Einstein. On the contrary, it is the mark of a really major step in thinking that when we have become used to it, we can no longer imagine how things were before that step. In spite of its, to us, almost obvious character, the principle of relativity at first had a rather rough passage. Such situations occur frequently in physics if a step is taken, logically compelling, forced upon us by experiment, and yet upsetting one of the cherished notions. That is what the principle of relativity did to the concept of time. As we will show in the next chapter, it has changed the concept of time in a way that seemed to be contrary to common sense. Actually, now that this book was in 1965, It's not fashionable to say quantum mechanics requires absolute time. So relativity has a lot of relative time. Quantum mechanics has absolute time. The two are in conflict. You can look up the Wikipedia entry on this. I've said the way to resolve this is there is absolute time, but variable clock rates. The measurement is actually distorted, and you have to put a correction factor. You can actually, I will argue, create, at least in principle, experiments within your own internal system, and you can determine what your absolute velocity is. And I'm going to have a discussion about radar guns with Dr. Dennis. We'll be working through things like GR here. And I owe him the courtesy to understand what is being said. I may disagree, but I owe him the deepest courtesy to study and comprehend and be able to at least articulate the mainstream points. And I actually don't know where he stands. I seem to recall he said he believes in absolute time also. So this is going to be an interesting discussion. The experience of everyday life. It may be worth digressing for a moment to discuss what is meant by common sense, and whether a conflict of physics and common sense is something to be expected. Common sense refers to the tremendous amount of experience we gain in early life that tells us such an enormous amount about the world we live in and the objects that surround us. Though possibly some elements of it are instinctive, the bulk of common sense is distilled experience. The experience we gain in those early years of life are naturally gained in our ordinary surroundings, with using the tools and materials that are at hand. We do not gain any common sense appreciation of the behavior of gas at 1,000,000 degrees because we do not meet that kind of thing in ordinary life, nor do we gain any appreciation of the view of the world one would have if one were speeding through the countryside at 100,000 miles a second, simply because it does not happen to us. On the other hand, common sense is a splendid guide in that particular field on which it is based, that is, the experience of everyday life. It is the task of the physicist to go beyond this, to devise and use instruments that enrich experience, that allow one to gain knowledge of objects and circumstances one would not normally come across. One would then expect that when the physicist, in his exploration of a larger range of experience than what has gone into the making of common sense, examines his results, he may find either that the impressions of common sense apply or that they do not apply. If they do apply, then it merely means that in his extension of range of circumstances, he has not gone beyond the validity of what was acquired in the narrower context. If he does run out of this set of circumstances, then naturally one would not expect common sense to apply. In fact, common sense would then be an unwelcome intruder, making it more difficult for us to adapt ourselves to these new circumstances than it might otherwise be. Adaptation to a new set of circumstances is always possible. Human beings are intelligent, which is equivalent to the statement that they are flexible. Once one has met enough of a new set of circumstances, one can order them and acquire a new understanding of them, in just the same way that one can learn a new language. It so happened historically that the physicist's instruments became sufficiently powerful to outrun the range of validity of common sense at the end of the 19th century and in the early years of the 20th century. Then, for the first time, results were derived clearly contrary to experience in our ordinary and very different circumstances, and a great deal of heart-searching and trouble arose. Nowadays, we know that this is totally misplaced. The farther we range with our instruments, the stranger the worlds we investigate, the more different they will clearly be from what we are accustomed to. The modern physicist, to follow Lewis Carroll, is used to believing at least two incredible things every day before breakfast. To put it again a little differently, the surprising thing surely is that molecules in a gas behave so much like billiard balls, not that electrons behave so little like billiard balls. To come back then to Einstein's principle of relativity, its fundamental importance is that it extends the Newtonian notion of relativity to all physics. All inertial systems are equivalent in every sense of the word. It is not only a question of pouring out tea in a jetliner being the same as pouring out tea at home, but it is also true that looking into a mirror in a jetliner, one sees the same as one does when one looks into a mirror at home. And I would say, you could also say, the unity of physics is unified by an absolute time and an absolute reference frame. It can only be illusion that it is all relative. Absolutism is, I think, the real key, and relativity is the illusion. People will cringe at me saying that. I hope I don't offend Dr. Dennis. But what will bear all this out is the math. We can work thought experiments with mathematics, and then, if not, the only limitation being practicality, whether those experiments can be carried out. But I can suggest some where we do use radar guns and cesium beam atomic clocks. And let's just say we have a quote-unquote clock that is more precise than cesium beam. We might be able to compute what the answer should be based on existing theory. The existing theory that is well established is the Lorentz transformation. I don't actually think it agrees with the way Einstein characterized relativity in terms of the first postulate. There's a disagreement there, and it is testable in principle. People don't realize that Einsteinian special relativity and Lorentzian special relativity have experiments that can't distinguish them at all. So far, I saw a number of 12 possible experiments. I'm going to propose a 13th. And it will be internal dynamics. Internal dynamics. That's what I'm going to bring before Dr. Dennis. Time, a private matter. Optics, dynamics. In fact, the whole of physics is unchanged by uniform velocity. It turns out, as will be proved in the next chapter, that the common sense concept of time does not fit with the principle of relativity, combined with the fact that the velocity of light is the same in all inertial systems. There is a subtlety here. The measured velocity of time. The measure, you could say it is invariant according to the measurement in the inertial frame. It may actually have an absolute velocity in an absolute sense. Remember, quantum mechanics demands that time be absolute, not relative. So I will say it's your measuring apparatus. You can determine if you're in an inertial frame that is distorting your clock relative to the absolute clock. I mean, this is the way to resolve the paradox between relativity and quantum mechanics. Just say your clocks are affected. Everything, all the problems disappear. And I know I'm going to get pushback on that, but look, there is a problem, right, between quantum mechanics and relativity. I'm just suggesting, hey, time is absolute, clocks are variable. Time is absolute, clock rates are variable. I don't think that's that hard, okay? So instead of the velocity of the light is the same in all inertial systems, the measured velocity of light the measured velocity of light. We have to ease ourselves out of the time concept of earlier days. It turns out that this is only seriously upset when one considers very high velocities, velocities not much smaller than the velocity of light. But in principle, the difficulty arises at all speeds. We have acquired the knowledge that if you have a watch, and I have a watch, and they are made by reputable watchmakers, and we synchronize them one at a time, then whatever you do and whatever I do, the two watches will always show the same time. However, this is a piece of experimental knowledge acquired in a very narrow context, viewed from the point of physics as a whole. For neither you nor I will travel with really high speeds at any stage. We must therefore contemplate the possibility, not to put it any higher, that this permanent keeping together of your watch and my watch applies only as long as we both travel very slowly. To suggest that because our clocks keep the same time when we both travel slowly, therefore they must keep the same time when we move at velocities close to that of light. It is obvious nonsense. We thus have to get used to the idea that time is a private matter. That is to say, my time is what my watch tells me. And I'm going to have to disagree right here. I said, your watch could have effects that my watch doesn't have effects. It could be the watch that's being affected, not time. Again, the axiom of quantum mechanics demands an absolute time. Therefore, Einstein can't be quite right, Sabine Hossenfelder, and others. Time is that which is measured by a clock. Time is that which is measured by a clock corrected for its absolute velocity. How about that? This is a sound way of looking at things. A quantity like time or any other physical instrument does not exist in a completely abstract way. We find no sense in talking about something unless we specify how we measure it. Oh boy, don't get me started. We find no sense in talking about something unless we specify how we measure it. Evolutionary biologists, think about that. We can't even define fitness, much less measure it. You think I'm making this up? Look at Lewontin, Santa Fe Bulletin 2003. Or Andreas Wagner, Robustness, Evolvability of Robust, something like that, his robustness book. Anyway, we find no sense in talking about something unless we specify how we measure it. Oh my goodness. It is the definition by the method of measuring a quantity that is one sure way of avoiding talking nonsense about this kind of thing. If therefore we enter the discussion of the nature of time with an open mind on the basis that in everyday life we do not actually test what happens to time when we move very fast, then we must be prepared for universal public time to break up into a multitude of private times. The root dependence of time. The possibility of time being private rather than public raises the question of the root dependence of time. In everyday life, there exist two different kinds of quantities which may be described as root dependent and root independent. The distinction between them is readily explained when we consider a journey across a hilly country. If we start in one town and drive across the hills up and down over various ridges to another town and keep account always of the gain of height and the loss of height in every part of our way, then the net amount of height we have gained is simply the difference in the levels of the town where we finished the journey and the town where we started. Had we followed a very different route starting and finishing at the same points, the net gain of height would be the same, as it must be, because it is simply the difference in the heights of the starting and finishing points. This is the typical example of a route-independent quantity. The net gain of height does not depend on the route chosen. On the other hand, if we use a milometer of the car to measure the distance between the two towns, then our route will matter very much. According to the way we travel, the mileage covered between the two towns may have one value or another value. The mileage is therefore a route-dependent quantity. This may sound a mere statement of the obvious, but the important fact is that all quantities of physics can be classified as either route-dependent or route-independent. He could have used a better example. Just say, okay, going from point A to point B, there is a distance. There is a minimum distance that is route independent. I know where he's coming from. This is what they call conservative and conservative forces. So let's say you're lifting a rock. Give another example. Let's say you lift a rock up to a tower, it doesn't matter if you used how you got there. Did you get up there by say a ramp to bring it up to the tower, or did you climb a ladder bringing the rock up? When you drop that rock, it's going to have the same kinetic energy when it hits the ground. Doesn't matter how it got there. All right. Consider as a route independent quantity the motion of a diesel train running a shuttle service on a single track line between two towns. If there is no wheel slip, the wheels of the train will be in precisely the same position whenever the train is standing at the same point, irrespective of how many forward and backward journeys the train has undertaken. Thus, if a chalk mark were put near the top of one of the wheels when the train was in its starting position, then whenever the train returned to that position, the mark on the wheel would be near the top. Thus, the position of these wheels is a route-independent quantity. We can contrast this with a route-dependent quantity, such as the level of fuel in the oil tank of this train, which clearly depends crucially on how many of these return journeys it has made since the tank was filled. How absurd it would be in ordinary life if we mixed route-dependent and route-independent quantities. If we mixed up route-dependent and route-independent quantities, is shown by the suggestion that, while it is quite reasonable for the railway to charge a substantial single fare, the return fare should always be nil, since one ends up in the same place where one started. Perhaps the rule should then be that you pay a fare when you go back somewhere, and when you return, you get back your money. Such a route-independent charging system would bear no relation to railway costs, which are strongly route-dependent. To the physicist and mathematician, there is all the world of difference between a route-dependent and a route-independent quantity. The crucial discovery of relativity was the route dependence of time, which, having been considered a public universal quantity, was naturally thought to be route independent. Of course, it is only the fact that time has become private rather than public that allows it to be route dependent at all. But the important point to emerge in the next chapter is that we cannot escape within the principle of relativity from the notion of route dependence of time. I'm going to try to remember what it is, how the Professor Bondi has articulated this. I need to respect the views of such an accomplished physicist, and if I'm going to criticize it. Now, am I coming out of my own criticizing Bondi? Well, quantum mechanics, time is absolute. There's a route independence of the absolute time. There is a route dependence of the clocks that need to be corrected so that it has absolute time. It can be done internally, I'm going to suggest. So now I'm getting to the heart of the matter, the nature of time. Oh my goodness, this is a long chapter. It goes from page 71 to 92. This is a 21-page chapter. So, let me see if I could break this up. The peculiarity of high speeds. Oh yeah, this is a long section. And a more complicated situation. Okay, so Bondi has 1, 73, 74, 75. Well, we've gone on for 38 minutes. I'm gonna and that was only 60 to page 69. So 38 minutes is about 10 minutes of reading. 40 minutes of reading, 10 pages. So I'm going to have to break up this into two sections, the nature of time. The nature of time is going to be a difficult subject. And there's a chapter on velocity, coordinates, and the Lorentz transformation. And this is where it gets fun. I should do exercises on the Lorentz transformation in non-natural coordinates. So I'm going to revisit this. In the meantime, let me just close out with some thank you for joining me. Glory and honor to our Lord and Savior Jesus Christ. We should be mindful of Him in all that we do. Lord, forgive me. I forgot to open with my. I should have opened the show giving honor and glory to You. Lord, we should acknowledge Jesus Christ in all our ways. So let's close this segment out. I may come back, and this just about put me to sleep, just reading this, such is the nature of physics. Therefore, it should be taken in measured quantities at a time. This is excellent reading, excellent suggestion by Dr. Phil Dennis, Dr. Phil. So with that, let's close out. Take care, and God bless you all.